Okay, I think it's 2 o'clock already, and I think we can make a start. We've already got 31 participants online, which is good, and I'm sure we're going to pick up a few more as we move into this. So this is the first of our webinar series, and we'll be sending out an emailer today with the 3 webinars that we're going to be having next week. So hopefully everybody will get those emailers, and we'll put it on Facebook and LinkedIn as well. Today I'm going to be talking about pressure management, he said confidently. And I'm going to talk a bit about pressure first of all, and how it affects leakage volume and burst frequency. And then in the second part, I'm going to talk about advanced pressure management and specifically pressure reducing valves, which are often the most common way that we control pressures in the network. Looking at basic PRVs, but then also moving into more advanced ways that we can control our PRVs. So if we look at the 4 pillars of real losses or physical losses that we, hopefully everybody has seen a lot of this before. It's the 4 main ways that we can manage and reduce our real losses. So we have active leakage control, so actively going out looking for leaks that are generally the underground buried leaks. Speed and quality of repairs to make sure that those leaks we find are repaired properly and to a good standard. Then we have pipeline and asset management. So this is where we have pipes that are just so poor that we just have to go in and do something to them, like reline them or replace them. And then the 4th one is pressure management. Pressure management is a bit different because it doesn't actually find and repair any leaks. But by controlling the pressure, what we actually do is we reduce the volume of water which is being forced out through the leaks in the pipe network. Now, if we look at the boxes in the middle, you can see that there's a big blue box, which is the current annual real losses. So this is what your physical losses are at the moment. So people might say, I've got 10 liters per second in this DMA of leakage, or they may say 20% leakage levels or whatever, but that's your current level of leakage. Then the yellow box, which you can see in the middle, the small yellow box, is actually your unavoidable annual real losses. So we can't feasibly get down to 0 on our leakage. There's always going to be a small amount of background leakage on our pipe networks. So the unavoidable is the level that if we did our real best, that's what we could get down to. But there's also another box, which is the orange box that you can see here, which is the economic level. Because as we're doing all of these activities, all of our active leakage control, pipeline replacement and refurbishment, repairs and pressure management, it's all costing money. And there needs to be a balance between how much we're spending compared to how much we're saving from the water that is being reduced, the leakage volume that's being reduced. So generally, most water utilities are aiming not for the unavoidable, but they're aiming for the economic level of real losses. Now, when we're doing active leakage control, pipeline management, and speed and quality of repairs, we're actually reducing the current annual losses, but we don't affect the unavoidable annual real losses. But when we do pressure management, it has the effect of not only reducing the current annual real losses, the current physical losses, but it also helps to reduce the unavoidable losses, the background losses. Because what we're doing with pressure management is we're reducing how much water is being forced through the existing leaks. When we do pressure management, we do it for a number of reasons. The first one is to reduce pressure. And even though we're reducing pressure, we still need to make sure that we're meeting customer service standards. And this will differ from utility to utility, country to country. Some may have a standard of 10 meters or 15 meters. And in some other places, they may have to be able to supply to a 4 or 5 story apartment block. So that's something that you need to consider when you're looking to do pressure management, is making sure that you're still meeting the customer standards or what is required by the customer. Another good reason why we often do pressure management is to actually open up other parts of the network. So if you reduce pressure, you can actually reduce the volume of leakage. And that means that you've got a volume of water which is still being treated at the treatment plant that can then flow to other parts of the network. So you may find that if you had an end of the network with very low pressure and you do pressure management near the top end of the network, near the treatment plant, the pressures at the end of the network will actually go up and improve the customer service down there. And probably the biggest reason why people like to reduce pressure is to reduce leakage volume. As I've mentioned before, it's one of the key pillars of the reducing physical losses, but we'll talk a bit more about that in a minute. The second reason is to produce a stable network. If you just have an open network, especially in a pumping system, you can have pressures that are going up and down all the time. And those variations in pressure going up and down all the time can really have an effect on the strength of the pipe. So what's happening is the strength is actually expanding and contracting just minutely, but every time there's a pressure spike or an increase in pressure, it expands. And when the pressure drops, it contracts. And that has the effect of creating fatigue on the pipes. And that fatigue will just weaken the pipes over time. Transients or pressure spikes are one of the key things that create pressure bursts. So by creating a stable network, reducing your transients, that will help to reduce the burst frequency. And I'm also going to talk a bit about that. Unfortunately, these days, transients or monitoring of transients is not something which is done too much by water utilities. And a lot of water utilities don't realize the sort of transients that they have in their network. If you're logging at, say, 5-minute, 10-minute, or 15-minute intervals for your pressures, you're not really going to be picking up any transients. You really need to be logging at sub-second intervals, often 128 times per second or 256 times per second to get a real visual of what the transients are doing. And both of those will help you to extend your asset life. If you can reduce the fatigue on the pipes, you're going to extend the asset life. And if you can reduce your burst frequency, you're going to extend asset life as well, which is one of the key things for a lot of water utilities. So the actual management of, or the relationship between pressure and leakage volume is not difficult. It's quite a simple equation, and it's actually a square root relationship between velocity and pressure. And it's almost like a one-to-one relationship. And we can plot it in a simple graph like this. And it's basically the relationship that says, okay, if I reduce pressure by 10%, I will reduce leakage volume by 10% as well. And this means that because of this ratio, one of the things you have to understand is it doesn't matter what the pressure is in your network. If you've got high pressure or you've got low pressure, pressure management can help you to reduce your leakage volumes. So for example, if you have 50 meters pressure in your network and you reduce the pressure from 50 meters down to 45 meters, you're reducing the pressure in your network by 10%. And subsequently, your leakage levels would go down by 10% as well. Alternatively, if you only have 10 meters pressure in your network and you reduce from 10 meters down to 9 meters, only a 1 meter drop in pressure, you're still reducing the pressure by 10%. And if you reduce it by 10%, your leakage volumes are going to reduce by 10%. So pressure management is something that can be done with all pressure levels, whether you've got high pressures or low pressures. And in fact, when you're at the low pressure range, small adjustments in that pressure can have huge effects on your leakage levels. But it's not quite as simple as the one-to-one graph that I'm showing there, the square root relationship. And that's because we have different types of leaks. Okay, we have the standard on the left side, which is the fixed area discharge. So these are holes, and you can see the hole that's been drilled in the pipe. So these are holes where the area of that hole will remain fixed for the entirety of its life, basically. So by adjusting the pressure in the pipe, you're going to reduce the pressure on a one-to-one basis. But if we look on the right-hand side, we actually have other types of leaks, which we would call splits or cracks. And quite often we would see this in plastic pipes, AC pipes, where the pipe will actually split along the seam. Now, what this happens is, as the pressure increases in the pipe, the split will widen and the area or the hole that the water is flowing out from will actually get bigger. And as the pressure drops, you're actually going to get the crack closing up a bit. So we would call this one the variable area discharge. And in most water utilities, you're going to have a mixture of pipe materials and sizes. And so you're going to have a mixture of the different types of leaks you're going to get. You're going to have some fixed area and you're going to have some variable area. Now, it was back in 1994, John May, I believe, who came up with the acronym FAVAD, F-A-V-A-D, which stands for Fixed and Variable Area Discharge Paths. And this basically was a formula which said, okay, the leaks in my utility are a combination of the fixed area and the variable area. So it's not necessarily a straight square root relationship, but it can be a multiple number of different relationships. And for every utility, you will have a different relationship than anyone else. And we call this the N1 value. And a lot of utilities will actually try to develop their own N1 value. To do this, you basically do a pressure step test. So if you choose one zone or one area and you go in at nighttime when you have pressures in your network and basically leakage levels only, you start to drop the pressure at the inlet to your zone in steps, and you monitor what the level of the flow drops by. And by doing that leakage level and the pressure, you can actually plot a graph like this, which will give you the N1 value for your specific utility or even your specific network. But most people would go for if they're just doing a cost benefit analysis to get an understanding, a basic understanding of how much savings they would get by doing a simple pressure management program, they would use an N1 of 1. But when you do that, and then you then put some PRVs into the ground, you may find that you're actually getting better savings than you predicted. And that's because you have a higher N1 value. So that's something to be aware of. When we're also looking at leakage volume is the first thing that we can look at with pressure management. But as I mentioned, burst frequency is another factor that is something that a lot of utilities have to cope with. Especially utilities in places like Asia, where I work, you will often go to these utilities and they will have thousands of bursts or leaks that they're actually having to find and repair on a monthly basis. And a lot of those leaks are new ones that have occurred in the last month. So that's what we would call the burst frequency. To stop that, we need to start looking at how do we reduce those transients in our network. The basic methods of pressure management, like putting brake pressure tanks in, pressure reducing valves, that sort of thing, they are going to help to get rid of some of that transients in the network, especially over long pipelines. You still have the issue of pumps. Pumps are one of the key factors for inducing transients into your network. And so it's very important to have some surge protection in your pipelines. For example, a surge tank or a surge valve. Both of those will be able to help you to reduce the effect of transients in your network. These sudden changes, they're going to give you the frequent bursting problem, but they're also going to affect the lifespan of your pipes as well. Some of the research that's been done has looked at intermittent supplies, which is the ultimate in terms of transients, because every time that a water supply gets turned off and then turned on again, you're inducing surges down your pipelines, which can be very high. And there has been some analysis done that shows that it can be more than 10 times higher bursts frequency in an intermittent supply than in a continuous supplied area. Now, if we're looking at pipes, you can see here, this is a sort of graphical visual look at how a pipe would work. You can see the arrows at the bottom are basically your design pressure. So let's say we had designed the pipe for maybe 6 bar, and our pressure is design pressure is sat at 6 bar. But then across here, we actually have a pipe strength. So maybe we've taken a PN16 pipe. So that pipe will start to fail when it gets to PN16, and there's a range of strength where it will fail, maybe PN16 to PN20. So we have a large factor of safety at the moment. Our pressures are at 6 bar, but we're actually got about a 10 bar factor of safety before we're reaching the strength of the pipe when it will start to burst. So when these pipes first go in, it's very rare for us to have bursts in our network. But then you start to operate the system and you start to get surges in the network, and also the pressures change a bit. So now you can see we're not at 6 bar, but we're up to more like 8 bar. And that's because our system is now operating in a different way, and we're getting closer. Our factor of safety is getting smaller. We also have other factors that can affect the pressures that we put into the network over time. So maybe this pipe, when it was designed 20 years ago, was designed correctly. But over the last 20 years, we've had some significant increases in demand. So we are now having to push more water down this pipeline, which means putting higher pressures in. Maybe there's been new developments in that area that have created this. But we've still got a factor of safety. We've still got about 3 or 4 bar factor of safety there. So our pipes should be okay. But the problem is that over time, the pipes actually start to weaken. So age will weaken the pipes, especially with different materials, and also corrosion. Traffic loading, for those pipes that are under the roads or close to the roads, those can actually affect our strength of the pipes. Ground movement, we do have people who are operating in earthquake areas, but we also have places like Bangkok and Jakarta, where the groundwater level is very high, and that can actually create ground movement as well. And then the other factor is low temperatures. So when we start to get ice, where water is freezing in the ground and then thawing, we're actually getting contraction of the ground, which means ground movement as well. All of those mean that the strength of the pipe is getting closer to the pressures that we have in our network. And that will then lead to burst frequency once those two start to overlap. So the first thing that we need to do is to actually try to reduce the surges. We need to identify those surges using transient loggers to try and find out where our surges are, and then try to fix the problem. If it's a pump, we can do that. If it's a valve, we can do that. If it's a reservoir opening and closing too fast on the inlet, then we can fix that as well. But we need to know where the problems are before we can start to fix them. And then the next thing is to actually reduce our excess pressure. Do we really need 6 bar pressure feeding into this area? Or can we reduce that from 6 bar down to 2 bar or 3 bar? So we need to be looking at our pressures and see, do we really need to be supplying 6 bar pressure to a housing area where the highest house is only 2 stories? They will really only need about 2 bar pressure to supply that housing area. Once we've done that, once we've reduced our surges and reduced the excess pressure, we've then got a nice factor of safety again between our system pressures and the strength of the pipe, the maximum strength of the pipe. There's been a lot of analysis that has gone on in terms of doing pressure management and trying to analyze the reduction in new breaks. These are just a few of the tests that were done, and you can see it's quite a global mix. But you can see that all of those utilities have had reductions in burst frequency, and many of them, it's more than 50%, which is a huge reduction in terms of managing your burst frequency, which then helps you to free up money for other budgets. If you're not repairing 1,000 bursts a month, but you're repairing 400 or 500 a month, you're saving half the budget that you would be spending on those repairs. Reduces the backlog. I laugh a bit here, but quite often you'll go to utilities and they'll say, yeah, we find about 1,000 bursts a month. And I say, okay, so how many do you repair? And they say, oh, well, we've got about 20,000 in our backlog. So are they ever going to be able to get it down to 0? Probably not. But if you can reduce the burst frequency, then maybe that gives them a chance to start to get rid of some of that backlog. It also reduces the rate of rise. So this means that some DMAs that maybe you were going into every 2 months or every 4 months, maybe now you only have to go in once every 6 months or once a year, because you've reduced how often the new leaks will form, and thus how often you need to go in and find the leaks and drop them back down again. And probably one of the biggest cost factors is extending infrastructure life. Because if you have a pipe which you think is only going to last you 30 or 40 years, but by putting in pressure management and reducing the burst frequency, you might get that pipe to last 60 or 70 years. So that is a huge saving in terms of the pipe replacement costs that you would have to spend. How long do these burst frequencies last? Well, there have been cases where it's been more than 10 years. So you put in pressure management, you reduce that burst frequency down. And as I showed you, the pipe, the strength of the pipe, okay, over time it's going to get weaker and weaker again, but it may be 10 or 20 years before you start to experience more frequent bursting again. There are quite a number of ways that people do pressure management in their networks. PRVs are a very common one, and I'm going to be talking a lot more about that in the next step. But other ways we can do it is through brake pressure tanks, reservoirs, or water towers. So a lot of gravity-fed systems actually use reservoirs to control the pressures that supply to certain areas. Rezoning. So if you have an area that has high pressures, or it's on a hillside with high pressures at the bottom, low pressures at the top, you can actually rezone that to have two separate zones and put pressure management in the bottom one so that you're reducing that pressure in there, and then you have got lower pressures for both zones. Trunk main control. So this is actually controlling the pressures at the trunk main side of things before it even gets into the distribution, which is quite good because generally our trunk main pipes are made of stronger material, steel, and therefore they can sustain the higher pressures anyway before it gets into the weaker distribution pipes like AC or plastic. Combined booster and PRV. So there are often zones where they have a high pressure, and the reason being is that at the end of the zone, there's a hill, and people say, okay, we have to supply pressure up to the top of that hill. So one other way of getting around that is to actually drop the pressure down on the flat bit and then have a small booster pump to boost it up the hill at the last part. Probably the saving that you would make in the leakage volumes would easily pay for putting the PRV in and the booster in a few months. Pump control. I think generally this is done now. I mean, most new pumps that go into the systems have got variable speed drives. There's very few fixed speed pumps that are out there anymore. Fixed speed pumps were the biggest problem in terms of creating transients in the network, especially when the pumps stopped. But most people now have got variable speed drives. If you haven't, it may be worth looking at your older fixed speed pumps and seeing how you can turn them into slow start, slow stop pumps using either a different drive, so getting a variable speed motor, or using a pump control valve to so that when the pump starts, it's pumping against a closed valve and then it slowly opens. Throttled valves, probably my biggest bugbear, because so many utilities will control pressures around their network by throttling gate valves. And it's the worst thing that you can do, because it doesn't actually reduce pressure properly, but it creates a head loss. So it creates a throttle where a head loss is created, which means at high demand, during peak demand, you're going to get high head loss. And at night, when you have low demand, you're going to have no head loss. So the only time it drops pressure is actually during peak demand, which is when you actually want higher pressure. And the other biggest problem is that people will go out and throttle these valves and then they forget about them, or they get buried, the valves, and you then have a system with so many different throttled valves in your network. And you'll get people that say, well, my pumps are pumping out at 6 bar, but the pressure in my network doesn't get above 1 bar. The main reason will be all of the throttled valves that are in your network that you don't know about. So let's move on to advanced pressure management. And I'm going to concentrate, as I said, more on pressure reducing valves, because they're probably the most common way that we look to control pressures, especially in our DMAs. So if you look at this drawing, you can see that we've got the treatment plant, which is pumping into a trunk main. And then we have 3 DMAs or zones underneath. Each of those zones would have a flow meter so that we can measure the flow going into the DMA, so that we can analyze it to measure leakage levels or night flow and then leakage levels. We can also do monthly NRW levels, and from that we can look at our commercial losses as well. So it's very important to set up these DMAs with meters. But you'll also see that after the meter, we've installed a PRV in each zone. And by that way, we can actually control the pressure going into each zone. Why do we do for each zone? Well, maybe because there's different types of users in a zone. For example, this zone might be mainly residential. So we want to have a different pressure profile than, say, this one that might be industrial or commercial. It is possible for us to just have one bigger PRV on the trunk main, as I mentioned earlier, and to control multiple DMAs. If you have DMAs that have similar customer demands and also the topography is fairly flat. Now, this is a typical basic PRV. So what's happening is we have a control chamber in the top of the PRV, and we have a rubberized diaphragm running across the middle of the PRV. And what's happening is, if we can pressurize the top control chamber here, it actually pushes down and closes the PRV. And if we release pressure from this top chamber, this diaphragm will lift up and the PRV will open. So by adjusting pressure in this control chamber, we can actually open and close or modulate this PRV to allow water to flow through. And what's happening is that as water flows through, it's creating a head loss, depending on how much the valve is throttled open or closed. To control the pressure in the control chamber here, we actually have a mechanical pilot. And that pilot has got a bolt in the top. And we can tighten or loosen that bolt to adjust what we want the downstream pressure to be. And once we've set the downstream pressure, 20 meters, 25 meters, then the valve will actually modulate open and close to maintain that pressure of 25 meters downstream. Now, this is what it looks like if we're looking at a period of high demand. Assuming we have 100 meters coming into the PRV, what we've done here is we've actually throttled the pressure across the PRV down to 60 meters. And what will then happen is, during peak demand period, you're going to get flowing through your DMA, and you're going to get head loss, frictional head loss through your pipes until you reach what we call the critical point. This is your minimum pressure point in the network. It could be the very end point if you have a flat network, or it could be the top of a hill if you have a hilly network. But at some point, you've got a critical point, which is where you're going to have your lowest pressure point. And you can see here that the pressure has dropped from 60 meters to 20 meters across the network, and that's by the frictional losses. But at night time, when we have almost no demand, you can see that there's almost no frictional losses across the network because the flow is very low. So what's happened is, at your minimal pressure point, the pressure has now gone up to 60 meters. So it was 20 meters during the day, but it's 60 meters at night. You see that the pressure on the outlet of the PRV has remained at 60 meters. That's the constant part. If we look at it as a graph, you can see the blue line that runs across the top is actually the outlet of the PRV. This is the fixed pressure on the outlet of the PRV. The green line is the pressure at our critical point, our minimal pressure point. And you can see that it goes down to 20 meters during our peak demand, and it goes up to 60 at our nighttime. And all of this hatched area is actually what we would call excess pressure, because we don't need it to be up this high. We could actually, if we could bring it down to 20 meters constantly across 24 hours, that would give us the most efficient use of our PRVs, because we're then looking to reduce any excess pressure. So with a basic PRV where we have a fixed outlet, yes, it's starting to give us benefits in terms of reducing our leakage volumes and burst frequencies, but we can do more. And the reason why we want to get rid of that excess pressure is that N1 value again, where we can reduce our leakage volume just by reducing that excess pressure. The first step that people often look at is to do multi-stage pilots, and 2 pilots are often the first step. So you can see in the picture, there's actually 2 pilots. The guy is adjusting one pilot and there's another one. So what we have here is a high pressure pilot and a low pressure pilot. So that would be maybe a daytime pressure pilot and a nighttime pressure pilot. And we would use a very simple timer device with a solenoid to switch between the 2. These timer devices are the things that people use for irrigation of gardens or golf courses or parks. When they want to switch on the sprinklers, they use these timer irrigation timers. We can use those same timers to switch over from a high pressure to a low pressure. And this is what it looks like. You can see the blue line at the bottom here is the downstream pressure of the PRV. So we have high pressure during the day, and then we drops to low pressure, and then it comes up to high pressure again. And we can use the timer to adjust the times when we want it to jump. So here we've got it at 6 o'clock in the morning. So it's going from low to high at 6 o'clock in the morning. In this example, it's quite interesting because they increase the pressure at 6 a.m., but then they drop the pressure again at midday. Then they increase the pressure again at about 5 p.m., and then they drop it again at 11 p.m. to be low during the night. So they haven't just got a daytime pressure and a nighttime pressure, they're actually mixing it up. And you can do that with the timer. You can adjust when you want there to be high, when you want there to be low pressure. You can also adjust the low pressure setting and the high pressure setting on the mechanical pilots. These are the similar timers that you could use. There's many out there. These are just a couple that I've used in the past. One of the good things that people like about them is they actually run off these 9-volt batteries that you can buy from any hardware store or even a 7-Eleven. Just 2 of these batteries, and you're looking at about 18 months life of these timers. So if you put these batteries in, you really only need to do preventive maintenance, about changing the batteries about once a year. And that's to be really safe. You could go for about 18 months and see how that goes. The other thing about these timers is they generally tend to be IP68, which means they're waterproof. And if you have PRVs that are installed underground in chambers where you have a chance of it getting wet or flooded, these should work okay most of the time in those wet or flooded chambers, as long as they're not underwater for a long period of time. Now, there are some utilities that actually look at putting in more than 2 pilots, so not just a high pressure and a low pressure. In this example, you can see they've got 1, 2, 3, 4, 5 pilots. So they've got 5 pressure pilots. And if I show you this schematic, you can see here, we've got 5 pilots. So you can set 5 different pressure settings. Each pilot has got a solenoid that controls when you use that pilot, but it uses only one of the irrigation timers. So that means with one single timer, you can have 5 different pressure settings. And so over a 24-hour period, you could actually have the pressure profiling up and down to whatever you want it to be. Why do some people like this method rather than going for a more advanced electronic? Basically because they see it as more simple. The more electronics that get involved, the more chance there is of failure. And the other thing is, if this does fail, the mechanical portion will take over and it will still operate as a normal PRV at whatever pressure was operating at the time it failed. Now, we've talked about using timers, electronic timers, to switch between high and low pressure. But there are mechanical ways that we can switch between high and low pressure. So if you look at this valve, it has a high pressure pilot and it has a low pressure pilot. And it has another pilot, which is what is called a demand switch pilot. So what this valve is doing is, you can't see it too clearly, but on the inlet here, there is an orifice plate. So what happens is, as flow goes through the orifice plate, it creates a very small head loss, less than 1 meter head loss. But as the flow increases, the head loss increases, and this pilot here senses the head loss across the orifice plate. When the head loss reaches 1 meter, it actually opens this pilot and the high pressure starts. Then when the flow drops, the demand drops below that 1 meter head loss across the orifice, then this closes and water goes through the low pilot and it drops to the low pressure. So this one we have high pressure and low pressure again, but instead of switching on time basis, it actually switches based on demand. So it could go to high pressure at any time in the day, as long as there is a demand that's required. That's quite interesting also if you have fire and you're worried about fire flows. If there was a fire brigade and they were to open up a hydrant, that demand would actually trigger the high pressure to open up. This is another one, which I'm not 100% clear on, but it also has a high pressure pilot and a low pressure pilot. It doesn't have an orifice plate this time, so if people are worried about the 1 meter head loss across the orifice plate that's created during the peak demand, I think this one works using this device on the top, and it's actually based on the opening of the valve. So as the valve opens up more and more, that means you've got higher flow going through the valve, and it triggers the high pressure pilot to open up. But there are a few different ways that you can mechanically control your high pressures and your low pressures. Now when we're talking about high pressure and low pressure, you've still only got 2 pressure settings, that high one and the low one. So there's still room for us to reduce even further the excess pressure. And the next step is to use modulation. And this is where the downstream pressure from the PRV is actually changed. So it varies constantly, moving up and down. to control our pressure at the critical point to get it more constant. Now we can do mechanical modulation once again. So there are some devices that use another orifice plate. So what happens is, as water flows through the valve, at higher flows, you're going to get a greater head loss. And if you get a higher head loss, it actually adjusts the pilot here to increase the pressure on the downstream side. If there's a low head loss, meaning low flow, this pilot will actually lower the pressure. So you can actually get a range of 2 bar between high pressure and low pressure, depending on flow rate going through the valve. And that will give you a more consistent critical point pressure using a mechanical pilot. We also have electronic modulation. A lot of manufacturers have got their own electronic controllers that go onto their valves. They tend to be actuators that fit onto their existing pilots. You can see this one actually takes the top of the pilot off and a new actuator bolts on. This one has an actuator that fits on top of the existing pilot. But what they're actually doing is they're turning a motor, which is turning the bolt in the top of the pilot to control the downstream pressure. And then they have their own electronic devices that can actually control how much the motor turns or what the downstream pressure is, dependent on flow. So they would need to be monitoring flow through the valve. And as flow changes, they would change the pressure downstream. There are also a number of third-party manufacturers that make controllers that can fit onto other valve manufacturers' stuff. And I've got a few of them here. They generally tend to be the data logger manufacturers. So quite often, what's incorporated in this is a data logger side of things so that you can log flow and pressure. And then also they then convert that into a PRV controller as well. One of the benefits from these things is that they tend to run off batteries. Because the data logger manufacturers have got a lot of experience on lithium battery technology, they've managed to make their systems work off of batteries for a long period of time, which helps if you have remote areas or areas where it's not so easy to get a power supply in. Now, with these controllers, both the manufacturer's ones and the electronic third-party ones, you actually need to develop a curve. So this is what we call a flow versus head loss curve. And so this is a bit of manual work where you actually have to manually work out at what flow you give to each pressure. So you would get some data loggers. You would put a data logger on the flow meter into the DMA. You would have a data logger on the outlet of the PRV and also at the critical point. And you would then create a graph like this of flow against hydraulic gradient or pressure drop across the DMA. This curve, this graph, you would then put into the devices like this, and they would then monitor flow. And as flow changes on the graph, they would then adjust the downstream pressure to adjust so that you would get a better pressure down at the end of the DMA. Now, with these devices, you tend to manually develop the graph and then you put it into the devices and then you leave it and forget. The problem then comes if you have a DMA which is changing in terms of demand patterns. So it may be that there's a new development. Maybe there's a factory that changes from making something which doesn't use a lot of water to maybe making paper, which uses a lot of water, or maybe a textile factory. So you're going to get changes in demands, even seasonal changes. So you're going to, in the summer, you're going to have different demands from in the winter. So this curve that we're looking at here is actually constantly changing. And when you're using a manual setup like this, you're not going to be accounting for that. You're going to be using the old data unless you go in and manually make a new curve every week or every month to account for that. So what the next step is to look at advanced modulation. So this is where we actually have permanent sensors that are installed in the field. So these sensors would be logging pressure, logging flow, logging upstream and downstream pressure, and also logging pressure at your critical point. These sensors would send the data back to a server, and that server would then automatically create the new curve, the new algorithm. So that way, if there's any changes to the demand or the system that you're working on, those changes that would affect the flow and pressure drop across it would be recognized. And this new algorithm would then be developed, and you can then send it via the cloud back to the controller that would then manage it. Most of the suppliers have actually moved forward from just the manual way to working like this. So there are lots of different ways where people will actually manage the data coming from this critical point sensor to the controller. Some will go to a server like this. Some will do what we call a closed loop, where this sensor will send a signal directly to the controller itself. There are different ways of doing it. There are benefits for both ways. This is the sort of curve that we're looking at. It's very similar to the curve that we had before for the manual, but it's actually based on a lot of data that's coming in from your data loggers. So you actually have a lot more data, and over time it becomes more and more accurate how you develop this curve. And that then goes into your controller. And by having this sort of system, you've now got the outlet pressure of the PRV, which is constantly modulating and giving you the most consistent pressure at your critical point at the end. And you've got almost no excess pressure. And with no excess pressure, you're then you're eliminating almost all of your excess leakage volume. Now, the next step moving on from that, which is only a few years now, 1 or 2 years old, is that people are now starting to look at DMAs a bit differently and saying, well, okay, a DMA may not have just one critical point. It may have a few critical points. So if you look at this zone, you see that if there's a residential area, maybe that would be the critical point during the morning peak when everybody wakes up, they have their breakfast, shower, and get ready to go to work. But then by 9 o'clock, 10 o'clock, maybe the industrial area becomes the critical point. So the critical point can actually move across a DMA based on demand patterns throughout a 24-hour period. So now, if you have a system where you have multiple pressure loggers in your network, this is actually a system by Inflomatics, where these sensors are actually looking for transients. So there are transient loggers that are helping to identify where you have transient problems in your network, but they can also help to monitor pressures across a zone and identify where the critical points are and how the critical points move. Now this data, it goes up to the cloud again, and the curves can be developed for multiple critical points. That can then go into your controllers, like they're doing with Clayval here, and that can then control the pressures in your network. So that is something which is still quite new and is still being tested in a number of areas, but it's the next step that people are looking at. So in summary, there are lots of ways that you can improve the performance of just basic PRVs. We've looked at timers, we've looked at modulation, mechanical, electronic, and advanced. So there's lots of different ways. They're all advantageous on reducing leakage levels, all to a different extent. So it's important that you actually do a cost-benefit analysis where you analyze each of the different methods to see how much it would cost compared to how much it would save for you. But you also need to consider that there are other benefits as well. Some of the electronic devices also have data logging capabilities, 3G or 4G communication capabilities, transient logging capabilities. So it's not just, when you're doing the cost benefit, you're not just comparing how much it costs with your leakage saving, but you're also looking at all of those other benefits as well. If you're reducing burst frequency, you could look at saying, okay, I'm going to include the cost that I'm going to save on repairs and possibly the cost of saving on pipe replacement as well, but that gets a bit more complicated. Well, thank you very much. I hope it's gone a bit longer than the 45 minutes that I thought it was going to be, but I hope it's been interesting to everyone. If anyone has got any questions, I'm here for a few more minutes, and there's a chat box that if people want to type in the chat, or if anyone wants, I can get them to speak the questions. I'll give people a little bit of time in case they are typing something. I did see earlier that somebody put a hands up or something for Zoom, which is, I'm still learning how Zoom works, but I'm not sure what a hands up means, but I think it means that I can then call that person to speak if they have a question. But, so if you have any questions and you don't want to ask them here, or you think of a question after we've finished, then you can always email me at gary@me.com. It was on the front slide, so you'll be able to look at it on YouTube later. And I will be posting this video that I've been recording on YouTube a bit later. So I've had a question from Andreas saying, from your experience, which of the pressure management techniques you describe is usually the most used among water utilities? That's a good question. Probably percentage-wise, it would be the timer devices. The reason being for that is because it's the cheapest version, and you get a very good rapid reduction in leakage volumes by cutting down your nighttime pressures. So a lot of utilities will actually start with that timer system, and then once they've got that in place, they will then look at more advanced techniques. There are some other utilities that maybe if they have very tough leakage reduction targets, they need to go deeper than the timer systems, and that's when you would need to look at the more expensive modulating systems. So Dale says, hi Gary, has the advanced inflomatic system you touched on been installed in Asia? There are some trials going on at the moment in Malaysia, which is the first country in Asia that's got the inflomatics going in. So that's going to be interesting to see what it reveals. I do know that there has been quite a lot of work in Australia with the inflomatics transient loggers. With detection services. So if anybody knows detection services, you could ask Stuart Stapley as to how he's found the results from that. Can we co-control more than one PRV in a zone? It is possible, yes, but you have, as you have with two PRVs, you have the chance of hunting again. So if you're looking at the timer systems, which are the very basic ones. It's very easy to put those onto multiple DMAs. Multiple PRVs feeding one DMA, because you just put a timer onto each DMA and you set the times when you want them to switch. When you move to the modulation and the advanced modulation, it gets a bit more difficult, because you could have the two PRVs that start to fight against each other. So I wouldn't say it's 100% works that way at the moment. I would say the best thing if you have multiple PRVs is to use the timer system. This is from Igor. I have a question about two-stage pressure. How bad can it be for pipes according to pressure changes, and what would be the max difference between high and low pressure? Okay, so with most PRVs, you can actually put a speed control valve that actually controls how fast it switches between high and low pressure. So if you're worried about it going from low to high pressure very suddenly and creating a surge, there are ways that your PRV manufacturer can put a little needle valve to control how fast the valve reacts. And this can then slow down how fast it goes from high to low pressure. As for how much between a high and a low, it can be anything really. It's up to you. I mean, I've seen it where it's only 5 meters difference between high and low pressure. And I've seen it where it's 40, 50 meters difference between high and low pressure. Obviously, where you have the greater difference between high and low, you have to consider that speed that it jumps as well. But that's where you would definitely need the needle valves. How much average pressure do you recommend for urban water supply? If it's generally, for most places, you're looking at about 15 to 20 meters, which should be enough to get to the average 2-story building. It depends a lot on how the water supply system is in your country, because if you have ground tanks, then you can actually have lower pressure because you don't need much pressure to feed into ground tanks. If you have roof tanks, like in Malaysia, you actually need enough pressure to get into that roof tank. So you need to have a think about how water supply goes into your system. Is it ground tanks, roof tanks? And also, is there some law where you have to supply to a certain level in an apartment? I know there are some countries where it has to be maybe 5 stories or 6 stories high, which you would be looking at something like 30 meters, I think, to get up that high. Hi, Gary from Junwei. Do you know good practice of transient measurement in Asia countries? Yes, there are. Most of the data logger manufacturers will actually manufacture transient loggers, so you can buy transient loggers. But at the moment, they tend to be sort of standalone loggers, which means that you program up the logger and you put it somewhere, and it logs at multiple times per second, and it records a very vast amount of data. And then you have to bring it back to your office, download that, and have a look at it. The next step is to actually look at how you can do it with multiple loggers, and looking at how you can communicate that data as well back to the field. So there are a few out there at the moment. There's on the trunk mains, there's a couple of trunk main ones. I'm not sure. I'll mention names anyway. There's Vicente, which is from Singapore, and I've forgotten now, but there's the one in the UK. Maybe Dale will mention it if he types it in and tells me their name, but I've forgotten their name now. But they do the trunk main, Cyrenix. So Cyrenix do trunk main transient logging as well. Vicenti and Syrinix both work, I think, they need a power supply because they're sending a lot of data back, so they would burn through batteries. And then there's another technology called Inflomatics from the UK, and they're actually battery-powered transient loggers that are used more for distribution systems. So they send data. I mean, I think Syrinix and Vicenti are continuous, so they're sending data back all the time. But Inflomatics sends the data back on an hourly basis. And they can then basically, if you say put 10 or 15 Inflomatics across one DMA, they can analyze the DMA and tell you where the transient is, the source of the transient is likely to be. Like I said, it's still in the early stages, so I haven't seen too much results, but that's what I'm hearing. What's the next question? Is it possible that N1 is 2.5? Yes, it is possible if you had a very bad pipe network. If you had some very old, poor quality plastic pipes that were just splitting everywhere, then definitely you could have something that was up to 2.5. Probably not very common, but it is possible, yes. Okay, so I've been corrected. Apparently Syrinix is battery operated and it sends the data in batches. So Vicenti is continuously online and is powered, but Syrinix sends in batches. Okay, I think that's the end of the questions. So I'm glad there's still 41 people on, and I saw there was about 50 plus during most of the presentation. So thank you very much, everybody, and see you all again at the next webinar, which will be on Monday in the US. David Earhart.